Good evening to all of you. Hello, I am Saikat Giri, your chemistry educator. Today we are going to take the second part of hydrogen bonding. In first part we have learned many varieties. Among them most important are how to count hydrogen bonds, what is hydrogen bond, which of the elements that are connected to hydrogen so that it shows hydrogen bonding. Today we are going to discuss about the types of hydrogen bonds possible, how it affects melting point, boiling point of a substance, as well as acidic and basic strength. So let's start with hydrogen bonding part 2. First part we are going to take, that is type 1 of hydrogen bonding. Type 1. What is type 1? Type 1 signifies symmetrical and unsymmetrical hydrogen bonding. First we are taking symmetrical hydrogen bonding. Symmetrical hydrogen bonding. We'll elaborately discuss about that. After that we will discuss unsymmetrical hydrogen bonding. Unsymmetrical hydrogen bonding. Here we will do comparative study in between both. Two type of hydrogen bonding we are going to discuss. Let's see. In case of symmetrical hydrogen bonding, as the name itself signifies, you can say that hydrogen connected with any element. Let us consider A connected with one element, hydrogen. Whereas we know that if A is electronegative, A will develop delta minus and hydrogen will develop delta plus charge. Let us consider it is making hydrogen bond with another element B, which is highly electronegative in nature. That is your B minus. Now what is happening? If I am considering the length between them is x1 and the length between H and B, that is x2. If symmetrical hydrogen bonding, we can basically say x1 equal to x2. If bond length is equal, then bond energy is also going to be equal. As a result, for them, E1 is also equal to E2. So, bond length equal and energy is also equal in case of symmetrical hydrogen bonding. Here we can say that hydrogen is present at the midpoint. We can say hydrogen is present at the midpoint. This is about symmetrical hydrogen bonding. Now what is unsymmetrical hydrogen bonding? What do you mean by that? Unsymmetry, it simply signifies their bond length is not going to be equal. So let's take, so in this case we are considering first case, what is that? Hydrogen connected with A and it is also connected with another element B. Let us consider this length is x3 and this length is x4. If we are commenting on the length, we can clearly see over here. In this case, this x4 is greater than x3. So bond length here is more in case of H and B. X4 is greater than x3. As a result, bond energy E3 is going to be greater than E4. As we know, bond length and bond energy are inversely proportional to each other. So we came to know that in unsymmetrical hydrogen bonding, hydrogen is not present at the midpoint, and in this case, bond length and bond energy are also different. Let's see another case. What is the value of bond energy? Generally, bond energy in symmetrical hydrogen bonding is greater than 42 kilojoule per mole. It is a statistical data we find out. So we can say that if it is greater than 42 kilojoule per mole, means it is a strong bond. In this case, if we are taking unsymmetrical hydrogen bonding, obviously we came to know that its bond energy is less than 42 kilojoule per mole. Third, and one of the most important point is which type of hydrogen bonding is observed in the molecule. Here, the type of hydrogen bonding observed is ion dipole interaction force. We know that there are several types of van der Waals force. To be more specific, 6 types. Among them, one of the most important variety is, we can say here, type of attraction force or van der Waals force is ion dipole forces. Type of ion dipole attraction force, type of ion dipole attraction force works here, and here the force is dipole interaction. It is dipole interaction force. So basically we can say two type of forces, one is ion dipole, another one is dipole interaction force. What is the benefit having ion dipole interaction force, and what is the example of that? Let us consider we are taking KHF2. Here K plus and HF2 minus. Except KHF2, KHCl2, KHBr2, KHI2 does not exist. Then why it exists? Why KHF2 exists? Let me tell you one of the most important concept about this. HF2 minus is the strongest hydrogen bonding found. Let's see, in KHF2, here also you can take a note that KHCl2, KHBr2 and KHI2, that does not exist. Does not exist. But KHF2 exists. Why it did so? Let's check. What happens in this case? For KHF2, the hydrogen bonding is like HF2 minus. How HF2 minus can be drawn? See, fluorine connected with hydrogen and it is connected with F minus. This is one of the strongest hydrogen bonding found. As a result, KHF2 exists. So in KHF2 we can see symmetrical hydrogen bonding. Because of that, KHF2 is a strong molecule and it exists. But in case of KHCl2, KHBr2, KHI2, hydrogen bonding cannot be formed. That's why we can consider that it is very unstable. But this is stable and exists. Next we are going to type 2 of hydrogen bonding. There we are going to discuss intermolecular and intramolecular hydrogen bonding. Intramolecular hydrogen bonding. So in the second part we are going to discuss intermolecular and intramolecular hydrogen bonding. Let's check out what is that. First we are discussing intermolecular hydrogen bonding. Intermolecular H bonding. Next we are going to discuss intramolecular H bonding. So two type of hydrogen bonding is there. One is intermolecular, another one is intramolecular. What is intermolecular? मान लो दो स्कूल के बीच कंपटीशन हो रहा है तो हम क्या बोलेंगे? इंटर स्कूल कंपटीशन. मान लो क्विज कंपटीशन हो रहा है तो इंटर स्कूल क्विज कंपटीशन. इंट्रा मतलब मान लो एक ही क्लास में बॉयज और गर्ल्स को डिवाइड कर दिया गया और बोला गया कि सेम क्लास. लेट अस कंसीडर आईआईटी ए बैच. तो आईआईटी ए बैच के बीच कंपटीशन हो रहा है तो हम लोग बोलेंगे आईआईटी ए के लेफ्ट साइड में जो बच्चे बैठे हैं और राइट साइड में जो बच्चे बैठे हैं उनके बीच कंपटीशन हो रहा है. तो ये हुआ इंट्रामोलिक्यूलर. तो हम बेसिक डेफिनेशन से समझने जाते हैं. अगर एक ही मॉलिक्यूल के बीच हाइड्रोजन बॉन्डिंग दिखे तो वो इंट्रामोलिक्यूलर है. अगर दो डिफरेंट मॉलिक्यूल के बीच हाइड्रोजन बॉन्डिंग दिखे तो वो इंटरमोलिक्यूलर है. मान लो दो वाटर मॉलिक्यूल कनेक्ट हो गए, दो NH3 मॉलिक्यूल कनेक्ट हो गया, दो HF मॉलिक्यूल कनेक्ट हो गया. इस केस में हम लोग बोलेंगे इंटरमोलिक्यूलर हाइड्रोजन बॉन्डिंग हो रहा है. मान लो कोई ऑर्थो कंपाउंड ले लिया, जैसे मान लेते हैं हम लोग ऑर्थो हाइड्रोक्सी बेंजोइक एसिड हमने ले लिया, ऑर्थो पोजीशन में OH और COH कनेक्टेड है, तो यहां जो हाइड्रोजन बॉन्डिंग दिखेगा उस केस में हम इसको बोलेंगे ये इंट्रामोलिक्यूलर हाइड्रोजन बॉन्डिंग है। तो इसमें ये बॉइलिंग पॉइंट को, मेल्टिंग पॉइंट को, कैरेक्टर को इफेक्ट कैसे करेगा एक बार चेक करते हैं। सो पहले हम डिस्कस करते हैं इंटरमोलिक्यूलर हाइड्रोजन बॉन्डिंग। तो जैसे आप लोगों को बताया, डेफिनेशन क्या लिखना चाहिए, हाइड्रोजन बॉन्डिंग व्हिच इज फॉर्म्ड बिटवीन टू डिफरेंट एटम्स or molecules, or you can say hydrogen bonding that is formed between two different molecules is known as intermolecular hydrogen bonding. For example, in case of water molecule, you can take one water molecule, another water molecule we are taking. So whenever two water molecules are present, we can show that in this case hydrogen bonding is observed in between oxygen and nitrogen. This type of hydrogen bonding is intermolecular hydrogen bonding. In between two NH3 molecules, you can say you have taken two NH3 molecules, NH3, another NH3 molecule is there. Two NH3 molecules we have taken. In between them, the hydrogen bonding is observed, is considered as intermolecular hydrogen bonding. So hydrogen bonding either represented by these lines or these lines, both have same meaning. Another case, in between para and meta compounds, intermolecular hydrogen bonding is observed. Para and meta compound means which position is para? Let us consider we have taken benzene. In benzene 1 and 4 position is considered as para position. Let us take nitrophenol. Para nitrophenol. Here we have taken NO2, here we have taken OH. How hydrogen bonding can be observed? Let's see. We can draw OH like O single bond H, and NO2 can also be drawn like N coordinate bonded O and double bond O. Double bond O. N can be drawn like this. And here one more OH can be connected. In this way it continued. So the hydrogen bonding is observed in between these two molecules. You can draw like this. I am erasing to show you properly. In this case the hydrogen bonding is observed. This is for para-nitrophenol. This compound is known as para-nitrophenol. So hydrogen bonding is observed like this. Here also one OH molecule. In this case one OH is connected. Understood? So you can draw like this as well. Here OH, we don't have enough space to draw. N, in this case OH is connected like this. It continued. In case of meta compound, meta-nitrophenol you take. For meta-nitrophenol, MnO2, N double bond O, coordinate bond O, and in this case OH connected, and here N double bond O, coordinate bond O, connected with another molecule. In this case we can see hydrogen bonding among them. So in case of meta and para compound, intermolecular hydrogen bonding is observed. Let's check for intramolecular hydrogen bonding. What is intramolecular hydrogen bonding? When hydrogen bonding happens in a molecule. So how can we define? We can write that hydrogen bonding takes place, H bonding takes place. Where it takes place? In the single molecule, or we can say within the molecule. Within the molecule, it is considered as intramolecular hydrogen bonding. Let us take, first we are taking para-nitrophenol. Now I will take orthonitrophenol. In this case OH is connected and NO2 group is also connected, and double bond O. This compound is named as orthonitrophenol. In case of orthonitrophenol, you can see hydrogen bonding here. So this is happening inside a molecule. So you can simply say what characteristics it will follow and what characteristics this will follow. Let's discuss one by one. In this case, I am erasing this. So, in case of para, molecule becomes little bit bigger in size. In this case, molecule becomes little bit bigger in size. As a result, their boiling point, if we are comparing, boiling point in case of para, it will be greater than ortho, because in ortho, intramolecular hydrogen bonding is happening. If we compare in case of meta as well, meta has also greater boiling point than ortho. If we compare volatility, if all three are compared together, highest para, then meta, then ortho. Volatility means any substance that can be in presence of heat easily transferred to vapor. That is the more volatile substance. In short, boiling point less, more volatile substance. Let's see. So volatility we can say opposite. Ortho has highest volatility, then meta is having less than para. So order is exactly reverse if we are talking about volatility. Let's discuss about another character for intramolecular hydrogen bonding. One more concept, one more very important concept. In which of the cases intramolecular hydrogen bonding is more effective? See, in case of 5 or 6 membered ring, generally intramolecular hydrogen bonding is observed. Not in case of 4 or 3 members ring. You can note down. In case of 5 or 6 membered rings, shows hydrogen bonding. Which type of intramolecular hydrogen bonding? Because angle strain comes for lesser members. Cyclobutane, cyclopropane, they are not very stable compound. So for them, hydrogen bonding is not going to happen. For these compounds, they become more stable towards hydrogen bonding. Crystalline nature. See, as the molecules are arranged in a single molecule, they are very closely packed. More packing, more crystalline nature. As a result, in crystalline nature, ortho is more crystalline than para compound. So crystalline nature highest will be in ortho, then para. Meta we will learn, we can't compare actually. Next. Another nature is solubility. Let us discuss the solubility. So, solubility depends on the extent of hydrogen bonding. If extent of hydrogen bonding is more, then solubility is more. In case of para compound, we have seen that extent of hydrogen bonding is better in comparison with ortho compounds. As a result, solubility of para will be highest. And when intermolecular hydrogen bonding is observed, solubility in the compound is better. Highest is para, then meta, then ortho, if we are comparing solubility of the compound. One more example for intramolecular hydrogen bonding, that is your chloral dihydrate actually. In case of chloral, what happens? We are going to see CCl3CHO. We know chlorine does not show hydrogen bonding. But in case of CCl3CHO, it is hydrated and the compound becomes CCl3CHOC. We can draw like this: CCl3, C single bond H, double bond O. Here two OH molecules are connected. So we can write CCl3CHO OH hold 2 when water is connected. It shows hydrogen bonding. Because of hydrogen bonding, 2 OH molecule in a compound is stable. Let's see. In case of CCl3, it is arranged like this: Cl, Cl, CCl3, CH, OH, OH. Now this compound is chloral dihydrate. In this case you can see here hydrogen bonding is happening in between chlorine and hydrogen. Because of this reason this compound becomes very stable. But if you take CH3, CHOH hold 2, you can see CH3 single bond C, one OH, another OH and H. This compound is not very stable. As a result, from here water is removed and we are going to get CH3 C double bond O single bond H. That is, we are getting acetaldehyde. We know that 2 OH group in a molecule is never stable, but in case of chloral hydrate exception happens because of presence of 3 chlorine atoms in the molecule. Understood? The comparison of solubility in water. Comparison of solubility in water. Let's see. So, when we are comparing solubility, any compound that shows hydrogen bonding is relatively more stable. So, the concept is any compound shows hydrogen bonding is relatively more stable. Relatively more stable, and you can say more soluble. So any compound shows hydrogen bonding generally more soluble in nature. Second property we can say, the second property of the molecules, that solubility is proportional to strength of water. Possible. So we can say that hydrogen bond is greater than dipole-dipole interaction force, or it also named as Keesom force. This is named as Keesom force. Some people name it as Keeson force. Both names are quite appropriate. Second case we are taking, that is solubility depends on the strength of hydrogen bonding. Depends on the strength of hydrogen bonding. What do you mean by strength of hydrogen bonding? So it basically means that 2 molecules you have taken. In that case, which is more capacity of hydrogen bonding, its strength is better. Let us take an example. For example, you have taken RNH2 and ROH. You are going to check hydrogen bonding in between them. So RNH2 arranged like this, and ROH you have, let us consider it is making hydrogen bonding with water molecule. It has lone pair, it is going to donate its lone pair, making hydrogen bonding with this molecule. Let us consider you have taken ROH and it is making hydrogen bonding with water molecule. So in this case, hydrogen bonding is happening in between 2. Here you can say, here donor atoms are different. As donor atoms are different, we need to check that tendency, or we need to check their strength. We can say that nitrogen is a better donor than oxygen. As nitrogen is a better donor, in that case, solubility of RNH2 greater than ROH. So what is the basic concept? First we are discussing about that hydrogen bond is relatively more stronger, more effective than van der Waals force of attraction. Which type? That is dipole-dipole or Keeson force. In this case, you can show any compound shows hydrogen bonding relatively more soluble in water. If you are taking solubility or hydrogen bonding strength, If hydrogen bonding strength is more, it is more soluble. RNH to ROH. If this type of case comes, in that case we have seen that hydrogen bonding is possible in both the compounds. So here donor atoms are also different. As donor atoms are also different. Here ROH, here H2O. So in this case, whenever you are following this type of cases or this type of case comes, you can consider which is a better donor atom, better solubility. Understood? Next we are going to see few more examples. Let's take one more example, very famous example. C2H5OH, we know it is an ethyl alcohol, ethylene glycol, CH2OH, CH2OH, and another one is glycerol. You know this is winter season, so in this time glycerin sabun is a lot in use. So this is glycerol. It is the main constituent for glycerin soap. So see, in this case we are going to check hydrogen bonding. So in this case, hydrogen bonding will be highest here. Why? Because you can see same donor atom. As a result, extent of hydrogen bonding need to check. Here more number of hydrogen bonding, here less, here least. As a result, chances of solubility is better in this case and least in this case. Let's take few more examples. Melting and boiling point, MP and BP. So in case of melting and boiling point, we can say melting boiling point is directly proportional to extent of hydrogen bonding. That is extent of hydrogen bonding. Last day we have learned how to find out how many hydrogen bonding is happening. Today we will understand what is the extent of hydrogen bonding. Let's see. I have taken H2O and H2O2. Last day we have read that in case of H2O, arrange like this. Two hydrogen bonding as a, here are two lone pairs as well. So 2 and 2, total 4 hydrogen bonding is happening here. In this case, for H2O2, check out H connected with O, another O connected with another H, 1, 2, 3, 4, 5, 6, 7, 8, 2 and 2, 4, and 2 hydrogen, total 6. Here 6 hydrogen bonding is happening. As a result, as here 6 hydrogen bonding is happening, melting and boiling point for H2O2 will be greater than water. So you can say that extent of hydrogen bonding directly proportional to melting and boiling point. Let us consider boiling point is asked for N2H4 and NH3. It is asked compare their boiling point N2H4. Let us check N2H4, nitrogen connected to nitrogen, 2 hydrogens are there. 2 hydrogens are there. For NH3, you check nitrogen connected with 3 hydrogens and 1 lone pair is there. In this case, 1, 2, 3, 1 lone pair. Here also 1 lone pair. So 1, 2, 3, 4, 5, 6. Total 6 hydrogen bonding is happening in this compound. In this case, 1, 2, 3, 4. 4 H bonding. Here 4 H bonding is existing. As a result, N2H4 has more boiling point in comparison to NH3. If it is asked that you compare the boiling point in between all these 4, what can you do? H2O, H2O2, NH3, N2H4. See, for H2O, there are 4 hydrogen bonding. For H2O2, there are 6 hydrogen bonding. For NH3, hydrogen bonding is how many? 4 again. For N2H4, hydrogen bonding how many? 6. So simply there is a tie. 2, 6 and 2, 4. Now how can you compare? Extent of hydrogen bonding you already have checked. You have counted how many hydrogen bonding is happening in the molecules. How can you answer this question? Let's see. In case of this, check the electronegativity difference in between the atoms. Here 2 oxygens are there. Here 2 oxygens are there. Here 2 nitrogens are there. As a result, oxygen is going to have highest boiling point or melting point, you can consider. H2O2 is highest. After that, N2H4 undoubtedly. Then we are comparing to H2O and NH3. You have seen H2O oxygen is more electronegative, nitrogen is less electronegative. So in this case, we'll compare with H2O and NH3. H2O has more boiling point in comparison to NH3. Very, very important question, how to compare the boiling point in between the molecules. Now we are going to see the same characters in different groups and how their melting points are varied. Let's check from group 14 to group 18. Group 14. In all the cases, we are going to check their melting and boiling point. Group 14, what are the elements? You can remember like Kasi, Gaye, Sant, Prabhu. Carbon, silicon, germanium, tin, lead. We are taking hydride of the molecules. That is CH4, SiH4, GeH4, SnH4 and PbH4. These are the molecules. For them, we are going to compare their boiling point and melting point. So, CH4, SiH4, GeH4, SnH4 and PbH4. Is there any case of hydrogen bonding? Answer is no. So there is in all the cases no hydrogen bonding. So melting boiling point, it will be proportional to molecular weight of the compound. From here you can see lead has highest molecular weight and carbon has least molecular weight. Also you can see down the group when you are moving, then one extra orbit is being added. As a result, their volume, density, molecular weight is also increasing. So in this case, PbH4 having highest melting boiling point in comparison to this. Let's check for group 15. In case of group 15, we are going to check. You are going to take NH3, New Zealand, Pakistan, Australia, sub-Bimar. You can consider like this. NPSA sub-Bimar. Elements are nitrogen, phosphorus, arsenic, antimony and bismuth. So for these compounds, we are going to check how hydrogen bonding is affecting their melting boiling point. Before going further, let me give you one important logic. Melting point is only compared in solid state. So whenever any elements, any compound's melting point is told, means they have considered it is a solid compound. So melting point compared only in solid state. Means we are talking about bismuth, BiH3 solid, NH3 solid. In that case you are comparing. Now see, in case of NH3, it shows hydrogen bonding. It has a greater extent of hydrogen bonding. As hydrogen bonding is more, so its melting point will be highest. Rest any of them, no hydrogen bonding. No hydrogen bonding. So we can simply say melting point and boiling point, or you can, here we are discussing melting point. So melting point, it is proportional to molecular weight, and among them BiH3 have highest molecular weight. So after NH3, it will come BiH3, after BiH3 SbH3, then AsH3, then PH3. So this will be the order of melting point. Boiling point, how can you compare boiling point for group 15? Let's see. For boiling point of group 15 molecules, what is the basic logic? You can check. In this case, boiling point, it is always compared in liquid state. It is compared in liquid state. So whenever you are comparing boiling point of a molecule, you have to check its liquid state. What is happening in its liquid state? Let me tell you one of the most interesting story. In this case, NH3 undergoes flipping in liquid state. So NH3 molecule, you can draw like this. NH3, in general case, we draw it like this. This is our NH3 molecule. In liquid state, it undergoes flipping. As a result, it becomes like this. So, their boiling point, besides being hydrogen bonding is present, is not highest. Here, molecular weight will overtake NH3, or you can say molecular weight overcome hydrogen bonding effect. So what will happen? Highest will be BiH3, then SbH3, now NH3 will come. After NH3, as usual, ASH3, and at last PH3. So this is going to be the boiling point order. If you are taking group 16 element, let us consider group 16 we are taking. That is oxygen, sulfur, selenium, tellurium, polonium, OS, Se, Te and Po. Let's see, in case of these compounds, if you are taking, this is H2O, H2S, H2Se, H2Te and H2Po. For them, how can we compare? Here also same logic is being followed. Only H2O shows hydrogen bonding. Only H2O shows hydrogen bonding. As a result, when you are comparing melting point and boiling point, in this case H2O having highest. After that H2Te, H2Po. H2Po is a molecule that is radioactive. So in this case we can consider next highest is H2Po, next H2Te as molecular weight is more, next H2Se and at last H2S. So this is the order for group 16 elements. We are taking group 17. What are the elements? In case of group 17, HF, HCl, HBr and HI. This is halogen family. In this case, if we are comparing melting point, we can say that HF undergoes hydrogen bonding, but it is very highly electronegative atom. As it is highly electronegative atom, it forms only one hydrogen bond. I already discussed in my previous lecture. So as a result, melting point will be highest for HI. So in this case also, molecular weight will overcome the concept of hydrogen bonding. So highest HI, after that it will come HF, then HBr, after that HCl. This is the order of melting point. If you are comparing boiling point, in boiling point HF will be highest. Hydrogen bonding is more preferable. After that HI, after HI HBr, then HCl. Then this is the order of molecular weight we are following. So this is all about the group elements, how it is affecting the melting and boiling point of the compounds. Let us take few more examples for hydrogen bonding that is related to melting and boiling point of the molecules. Let's see. For example, I have taken H2O and D2O. We have taken two isotopes which is going to have both shows hydrogen bonding, both have a better tendency. But in case of D has more molecular mass. As a result, its boiling point is highest. So we are comparing few more questions with boiling point. Second question we are taking for H2, D2 and T2. In this case, molecular weight is on the logic. T2 then D2. Let us consider we are taking acetone. CH3 is COCH3. Acetone taken. CH3 CONH2. This is amide taken. And CH3 COOH acid is taken. For these compound, it is asked hydrogen bonding. What is the boiling point order for them? Check out. In this case, CH3COH, it is having C 1, 2, 3, 4. So 2 lone pairs. Here also 2 lone pairs. Total 4 and 1 OH bond. Total 5 hydrogen bonds. In this case, NH2 2 and here 2. 4 hydrogen bonds. In this case, no hydrogen bond. As a result, it is having more boiling point. So these are the logics to decide hydrogen bonding. Let's take few organic compounds as well. We have taken benzene. Let's compare benzene. With benzene you take pyridine. With benzene we have taken pyridine. And another compound we are taking that is named as pyrrole. In this case, which of the following compound having more boiling point? Let's check. Here no chance of hydrogen bonding. In this case, one lone pair is there, one hydrogen bonding can be formed. Here in this case, one lone pair hydrogen bonding, one hydrogen. So two hydrogen bonding can be found. As a result, pyrrole is having more boiling point in comparison to benzene and pyridine. This compound is pyrrole or pyrrole, this is pyridine and this is benzene. Another compound, in case of simpler alkanes, if you take, for example, you have taken CH3, CH2, CH3, that is named as propane. You have taken CH3, OCH3, that is ether, and you have taken CH3, CHO, and one more compound you take, CH3, CH2, OH. We have taken aldehyde, ether, alcohol, and normal compound. Which is going to have highest boiling point? Let's compare. In this case, OH is connected. You can see 1, 2, 3, 4. So 2 and 1, 3. 2 lone pair on hydrogen. 3 hydrogen bonding can be observed in this compound. If you draw CH3CHO, CH3C double bond O single bond H. 1, 2, 3, 4. So 2 and 1, 3. In this case also 2 and 1, 3. Here C. CH3CO CH3. There is no chance of hydrogen bonding. And here also no chance of hydrogen bonding. But molecular mass of CH3O CH3 is more. So it is greater than normal compound. CH3CHO and C2H5OH, it has most hydrogen bonding. As a result, this is highest boiling point, second highest, third highest, and fourth. So these are the basic logics of hydrogen bonding by which we can decide which molecule having more boiling point, which is having less boiling point. Today's last application we are going to take, that is comparison of acidic strength. We are going to discuss comparison of acidic strength. Let's see. For example, we have taken one acid, that is HA. Minus H plus, it becomes A minus. It is an acid. We know that when H plus is removed, it becomes a conjugate base. So it is the conjugate base of the acid. More stable the conjugate base, more will be the tendency for going forward for the reaction. Acid will be more stronger. So what is the logic? The logic is more stable the conjugate base, more tendency for the reaction to move forward. As a result, more acidic the compound. So we are going to follow this logic to decide acid. Salicylic acid as the example. C OH COOH. That is orthohydroxysalicylic acid. Another example I am taking, that is metahydroxysalicylic acid. COOH. Let's take their conjugate base first. So we know that this is more acidic hydrogen, so it will be removed. So it will become C double bond O single bond O minus. And you can draw it like this. So hydrogen bonding is happening in between the molecules. But in this case, there is no chance of formation of hydrogen bonding. As a result, acidic strength is more for orthosalicylic acid rather than metasalicylic acid. Another example you can take, that is maleic acid. Maleic acid and fumaric acid. For maleic acid, COH are connected in the same side of the double bond. So COOH and COOH. This is our maleic acid, and in another sides hydrogens are connected. So whenever H plus is removed from the molecule, this is removed, it becomes O minus. As a result, in between the molecules, hydrogen bonding is observed. This is maleic acid. It is a cis product. Same side, so it is cis. Its trans product is fumaric acid. In fumaric acid, arrangement is like this: C double bond C, hydrogen, here COOH is connected, and in this case, here COOH is connected, here hydrogen. Any of the case, it becomes minus. So here, no chance of hydrogen bonding. As there is no chance of hydrogen bonding, in case of maleic acid, it is more acidic than fumaric acid. Another example I am taking, and it is the last example of today's class. Let's check. We are taking benzoic acid. Now orthohydroxybenzoic acid or salicylic acid. Another one is two OH are connected in ortho position. Question is, which is most acidic? Last one is most acidic. Why? Here chances of hydrogen bonding is more. This is highest, this is second highest, this is third highest. So basically, I think you have understood all the logics of hydrogen bonding, how to decide melting boiling point, how to decide how to count the number of hydrogen bonds, how melting boiling point affects in different groups, and how to compare the strength of hydrogen bonds. I think you have understood the concept. If you understood the concept properly, please like and subscribe, and also help me to grow, and let's learn and help people to learn. Thank you everyone. Have a good night.